Okay, so thanks everyone for being here today. I'm Eduardo Lemos, and I'll be presenting FACT, a functional domain-specific language for continuous time modeling. This is from my master's program that I'm doing in Brasilia, Brazil. And this is actually a second inline work that started with Edu Medeiros, one of my supervisors in his 2018 work. And this also, by the way, was my 2022 final project during graduation. So let's just get started. So there are many systems that uses continuous time, including this guy. So this is a modern fighter. Its name is Gripen E, and it's a Swedish fighter. And coincidentally, Brazil imports this guy, right? And there's two words coupling when a pilot is managing a Gripen E. It has the physical world, which is the control surfaces, and the cyber world, which is the computer that is embedded in the fighter. And this guy has a special property. You cannot pilot this thing without a computer because the physics on this one just go crazy. And of course, because this is not enough, we just throw a human in the loop just for fun. So there must be some synergy between the two worlds. And for the most part, we already addressed the continuous part of this problem with these. So these are what we call the mathematical description that models that system, and we used a classical framework called differential equations to describe them. So in this mathematical language, we have state variables, x, y, and z, and they describe the system state. And we can combine them with some arithmetic operations and constants. And of course, there are variations of the systems, such as being linear versus non-linear. And this is not a non-linear system because you cannot decouple the variables from each other. So this is the final result of that specific system that I just showed. And so far, so good. But there's a problem, right? We want to use computers to get to this result. We don't want to calculate by hand the system. We want to use computers as the tools. But we want to be here, right? We want actually to live in this world here because of some properties of interest. But our tooling forces us otherwise. So our work, Edu's and ours today, is to attempt to live most of the time in this world using a domain-specific language. And then today I'm going to explain the wiring that goes under the hood to make that happen. And that's our goal. But to reach that, we're going to backtrack a bit and talk first about legacy, right? So any intellectual work has legacy, which is a natural phenomena, and that's what Mr. Churchill noticed back in the day. And it's very natural, right? The future generations should use what the predecessors have discovered, and that is the most common way to make progress. But however, this put us at the risk of being legacy blinded, right? So we need to ask ourselves from time to time, what happens if we step back? What if we try to gather a new abstraction from scratch? Of course, this is not to say that every single thing that we are working today does not hold value. Of course it does, and we should keep studying it. But our work is an exploration of a new set of ideas. And so throughout this talk, let's go with the mindset that this is a new thread of thought. This is a completely new thing. This is something different that we are proposing. And with that in mind, something that we cannot be blind is the notion of time. Because in continuous time, this is not a measure of performance. This is a measure of correctness, such as what Edward Lee is talking about here. So this is not about being fast or slow anymore. Time, it doesn't have the semantics of fast and slow. It has the semantics of right and wrong, which is a completely different mindset in normal general purpose computing. So I would like to show you the end result. So this is where we're gonna start from the left and go to the right. So on the left, I like to call that dreamland. So that this is where we would like to be. And on the right, we have the domain-specific language that we are proposing, which is embedded in the Haskell programming language. And I think they look a bit similar, but the right one still has some noise that we would like to remove if possible. This domain-specific language takes advantage of Haskell's main features, such as the type system and the type classes system. And we are rising the bar here in terms of level of abstraction. So we're not going to go through low-level details such as C or Fortran. And in fact, I think this can go that much further, because if the other thing I want to show you is the best outcome of that, which is like Fact 2.0. And as you can see, there's even less noise to worry about. And it's all the noise, it's all gone magically. And now we just have the differential equations, initial values and constants, and some functions to do the integration. So we are closer to dreamland, and that's good. But let's not get ahead of ourselves. So today I'm gonna try to portray some intuition to you to get some intuition about this one, because we only can judge something as noise once we understand it. Why? So that's what we're gonna go today. So everything starts from Cloud Channel, right? So Channel is well known for his history of sampled systems. Before those contributions, he worked as an analog mechanical operator of an analog computer, sorry. And he developed a theory to formally explain the capabilities of the analog computer, and he coined that machine as GPAC, the General Purpose Analog Computer. And GPAC is based on 4 basic blocks. These 4 units are 4 axioms of his formal system. First, there's the constant unit, which basically generates an output k for all moments in time. Then there's the adder and the multiplier units, and they do sum and multiply arithmetic operations to choose signals at a specific moment in time. And these 3 units, we call them pointwise or combinatorial operations, which means that they do not involve any sort of memory. They don't remember anything, they just do the math. In contrast, this unit here, which we call integrator, is the one that handles memory in the system. This 4th unit calculates the mathematical integral of 2 provided inputs, in which one acts as the integrand and the other one acts as the variable of integration. Time can also be used as a variable of integration. These units can be interconnected in a specific manner, called composition rules. The first rule is that these pointwise or polynomial circuits AK can have multiple inputs, and each one of them should be time or the output of an integrator, which I'm calling it YK. Next, there is a rule about the integrators. Each integrand input of the integrator should be generated by an output of a combinatorial unit, a pointwise unit. Each variable of integration of the integrator is the time input. So you're basically grabbing the output of the combinatorial ones, pumping that, and doing an integral on that using time. So one of the worries when designing FACT is that it resembles the GPAC concept, with both the basic units and the composition rules. Ideally, for a given system model in FACT, a GPAC unit exists, following Shannon's theory. I need to clarify something. We didn't prove formally with like a proof assistant or anything that this mapping is one-to-one, but that's certainly something that we invite anybody to help us with, because we would like to perceive this formal approach to actually have correctness in like the Haskell code is actually mapping all the GPAC theory that Shannon did. And this is especially important in the modern age because there's a lot of ad hoc approaches going on. So we would like to get away from those. So these are the contributions we grabbed from Shannon: the GPAC, the basic units, and the composition rules. Later on, we will see how the abstractions that Haskell provides fits all these things. And the next main contribution actually came from one of the authors, right? So one of his vacations, Gil had a very eureka crazy moment, and he noticed in front of his own eyes what would be what he would coin continuous time in his 2018 work. And what was Gil's idea? What does it mean to say the time is like a blender? I'm glad you asked, because it works like this. So an operator configures the system, closes the lid, plays start, and it begins the continuous process. When it's done, the lid can be opened, the operator discretely changes the system for another round. And our paper does not discuss the interaction between continuous and discrete, but spoiler alert, that's definitely something that we would like to pursue in the future. So in order to achieve this, in his 2018 paper, Edu was inspired by the work of Edward Lee and Alberto Sangiovanni, both being highlights in the modeling-based engineering space. Fact also, as a follow-up, also follows some ideas that are described in the paper. So here we have it. The two main abstractions that we settle when backtracking and studying things from the past. And for this work, because we will only be exploring the continuous facet of the blender, we will only focus on GPAC for today and how Haskell allowed us to make that into fruition. So it's about time. Let's go gather some intuition about the operational semantics, about how it works actually. Because here me talking, you can just believe me, it would be just magic, right? So let's start. So for starters, we need to talk about functions, because the main abstraction languages like Haskell use are functions. And what are they? This is the visual representation of a function. A mathematical function is a mapping between two sets of values. So for instance, let's take a look on this function. It maps a double value to itself. Incrementing a double value is a function of this sort. But these sets are hard to remember without semantical names, right? So let's name them. So now we have a function that takes time and produces an outcome. Function programming uses functions extensively. In fact, it's called that for functions to be treated as high-class citizens. And what does that mean? Long story short, you can think of treating functions as plain values. You can manipulate them, combine them, and do what you would do with normal values in imperative languages. So the underlying mechanism of fact is, not surprisingly, a function, right? However, it's not a simple function like this one. It looks more like this. This function picks something called parameters, and that models time, and it's composed out of four things, and returns the weird thing on the right. I would like to go through two out of these four things. First, we have a solver, which contains specific configurations for the numerical process that fact will use throughout the simulation of the system. Here we have things like the integration time step, the integration method that we're going to use. And I should emphasize that this means that this type contains what usually a driver would know, a driver of the simulation. The driver would know the method and all the solver configuration. No. Here, this function itself already knows the configuration necessary to do the numerical method. And second, we have the interval of the simulation. Again, another drive, usually put in a driver backpack. This is completely within this function as well. So the simulation throughout all its process knows when it begins and when it ends. Next up, we have this weird thing as the output of the function. Simply put, the A in there is how Haskell handles generic programming. And the other I/O part it will allow us to make side effects, such as using memorization strategies, which, spoiler alert, we will. We call this function a CT machine type, a continuous time machine type. Now it's time to GPACanize it, right? So do you guys remember what do we need? We need 4 basic units and composition rules. Let's start with the former. So in Haskell, there is an interface called applicative. And that will do the trick for us. You know why? Because this function allows us to pick something and put inside something else. That is exactly what the constant unit does, right? Which is for every single moment in time, we're going to return an output k. So peer does this precisely. The other member of the applicative interface is this operator here, which funnily enough doesn't even have a proper formal unified name throughout the community. So I'm going to call it apply just for simplicity. This guy would do kind of the same thing that we did before, but with non-unary operations. And do we have non-unary operations that we care about? Of course. We do have addition and multiplication. So this apply function from the applicative interface allow us to do binary or other arrays of functions with the CT machine type. So now we have those. And so far, this is what we have, right? So we have these three units. But something feels a little bit off, right? Where's the integrator? Where is the guy with the memory? Where's the guy that will do the heaviest math? So the integrator uses a different type that we're gonna also use. So this is representing it visually. It comprises two things, one of those being the initial condition of the system. So where is the initial condition of the ordinary differential equations? And also a pointer to a mutable state. This state is going to be where the values are be computed using the numerical methods. Now we're going to make an interface to manipulate these integrators because we have them, but how are we going to use them? So we inspired ourselves using something from the database environment called CRUD, and that stands for create, read, update, delete. So for each one of those, I'm going to create a function aside from the deletion, because we have garbage collection in Haskell, which means that we gain that for free. So the create integ function creates an integrator. This function allocates memory region for the integrator. It creates a pointer for future access. It has the initial condition of the system, represented by the CT machine with a double value. And it's also saved into an integrator, the initial condition. The CT integrator value, it's a structure that can change the state of the integrator over time across the simulation, right? And it resembles the idea of a state machine because of that. The read integ function gives us a state variable. This variable is used to access the integrator's current state. So I'm going to basically have like a way to look inside it. In other words, this is basically giving me a bridge to the integrator, right? Because how I'm going to look into it, I need to look into it. And finally, this is the update function, the updating tag. It picks an integrator and a combinational machine represented by a CT machine with a double value and wire them together. Potentially, a feedback may appear, like in this example. This, however, is a special there's a special detail about this function. This is where the numerical methods live, right? So this is where we decide how we're going to do the numerical part. And there are three available methods currently, the Euler method and two methods from the Hujikuta family. Other methods can be added in the future, no problem. This is completely orthogonal to facts execution model. How many methods or which method you're going to use. This is basically just like you see on the screen right now. And these algorithms, Euler, Hujikuta, they require extra information that require changes in the design of the CT machine type. And those were what I was talking about before, the solver configuration things. And so this is like the core of the operational semantics. This is where the magic, the deepest magic happens. So if you go back to the model, we can see these functions in action. But of course, there's too much here. So let's go step by step. So first, we create the integrators, right? The integrators receive the initial conditions, right? So all of them will start with value 1 from time 0 in this case. So this is where when the integrators are put into existence, right? So on the left, you're going to see the code, and then we're going to try to see at each line of code what is happening in relation to the GPAC one. So at this moment, these lines is where those boxes on the right are being born. Then we get the state variables from these units. We are getting a way to look inside them, right? We are getting a way to look inside them. With, of course, the read integ function. Then we have polynomial circuits that are to create constants with adders and multipliers and stuff like that. The subtraction is being done by simply multiplying -1 to a positive value and then doing a sum operation. That's how we are doing subtraction. And some of these combinatorial boxes are the output of integrators, right? Then the update integ function wires these pointwise operations as the input of the integrators. And then finally, this last line creates a state vector, which basically creates a vector with all the available state variables, well, with the state variables of interest. And we are combining them in a single input instead of having them have a multiple output return. And as we saw, these functions were inspired by the GPAC model. And these are the pieces that we have now. In the paper, we describe in detail how the composition rules are also being mapped using the two types, CT machine and integrator. But I think the intuition with the basic units is enough for this talk. And from here, we will go through a guided example for even better understanding. So now that we understand how to create a model, we need to go through how we can run it, right? So you have the description of the model, and now you want to see the results out of it, right? So we need an executor of the model, which we call a driver of the simulation. This driver does not know any configuration or mechanism of the system. It will just make it run, because as we saw, the CT machine already has the required information, such as the time interval that we're going to use and the solver's specific configurations. This driver works throughout the domain of iterations, and this is executed in a recursive manner. So our driver works in a particularly unusual setting. We ask for the state of the model at a specific time, and we leave to the model to decide how it should get there. So it's like the blender again, right? So you're basically closing the lid and pressing go at this moment. So in this particular example, let's suppose to calculate the time we asked, we need 5 iterations. When calculating the result of the 5th iteration, the previous one becomes necessary, and the system will evolve in a recursive pattern. This pattern happens again and again and again until we reach the initial condition of the system. We are basically backtracking in time. When the base case is reached, this recursive process folds until it gets back to where it started, right? The driver domain, this that I just explained, is one of the 3 orthogonal domains that FACT traverses. So we have functions implemented in Haskell to go from one to the other, right? But again, this is more like implementation details. So we have, aside from the driver's domain, we have another domain which contains where the solver methods do the math. It uses a discrete time axis to calculate the differential equations. Discrete time depends on the time steps or time or deltas. A time step is a time slice that is used to move along the axis. This solver can be totally blind for certain arbitrary times, such as tx, depending on the time step. And finally, there's the domain of the real things. There's the domain that we're actually interested about, which is the continuous time domain. So this is the domain that we want fact to end up, right? It can traverse whatever in the middle of it, but at the end, something needs to happen to go back to where we want to be. So we have this as the exact scenario. So, but there's a big problem, right? Because until now, in the simulation that I just explained, we are not doing that. We are just living in the iterations, calling the solver, and in this discrete time when calling this when calling the driver, sorry, and in the discrete time when calling the solver. From the physical domain, we go back and forth between those two. But that means, of course, that we need to go back at some point. So the conclusion is that until this point, we didn't achieve the goal. We didn't achieve what we wanted to achieve. So we need a way to get back to the physical world. And our goal is to know the system state in any arbitrary tx inside the continuous time domain. Anyone. We need a way to migrate from the known domains back to the continuous one. And to solve this problem, FACT added an interpolation mechanism. So we use reachable points from the solver domain to calculate a linear interpolation that puts us back to the continuous domain. Of course, using linear interpolation is not going to be perfect, but this is something that we can improve upon because we can just change the interpolation mechanism to something else, another orthogonal aspect, right? And now that puts us back to the continuous domain, which means that now we are effectively solving what we wanted to solve from the beginning. But of course, right? Things are never easy. Something always goes back to put a gotcha on your face, and this was a big one. This was a big one. It's very slow. You may ask how slow, and I'm going to tell you 6 hours to 8 steps. Right? 8 hours to 6 steps is a big deal. So, and I don't have the most baller system in the world, but I think it's a little bit unreasonable, like 6 hours for 8 steps. And why is it so slow? That's a good question. The answer, long story short, is that the whole recursive process, doing the backtracking and folding that is very expensive. And it may be also because of the laziness of Haskell. If it would be strict, maybe that would be better. But it would be bad anyway. So this folding is happening every single time. Every single step calculated is going back to the beginning, back to the beginning. That means that we are wasting resources, right? So what about saving those things for future use? Once you calculate one, you calculate them all. So that's what we did. We added a table in memory, and that's where the effects are required. And this memorization approach that we used using a simple table is also orthogonal. You can use any sort of caching process or memorization strategy that you may please to use. So this saves the previous iterations in this table. So instead of recalculating it back to the start, you just do a lookup, which is a lot faster. How much faster? This faster. So now we are talking 1.5 hours for 10 million times faster. So now we do in less than 2 hours, we do 100 million iterations. Just that. And look at the scale. This is not as slow as before. So the conclusion is that, doing memorization is a lot faster. Yeah, of course. So here's where we finish. So this journey that I just did with you guys, I explained how to translate the dreamland mathematical description of the physical system into an executable model. This domain-specific language, FACT, is inspired by Shannon's GPAC concept and the Blender concept from Edu. We went through the mechanism to make this possible. And that included going from the discrete time domain to the continuous time domain using interpolation. And finally, we made some optimizations to make it a little bit more usable, right? But again, I need to emphasize the final goal is to actually have this, which is no integrator at all. There's the entire noise of the integrator is gone. And I hope we are close to me ever presenting how this came to be, right? How is this even possible to get rid of the integrator? So in terms of model-based engineering, what would the process would like with FACT? There is a system description that starts the process. In our case, the mathematical differential equations. And we're going to transform that to an executable model. And that's where FACT joins the party. The plan is that we use FACT to make a an executable proof of concept. And then you're going to go back and forth between the mathematical one and FACT and improve your model, improve its description and its specification. You will be iterating to the model, refining and improving the description every single back and forth. And then you're going to go to validation. So after you are happy with it, you're going to try to validate. So in our case, we are validating it via simulation, which is not 100% ideal because we would like to validate with like semantic preserving iterations, which would require a more formal approach to this. But validation via simulation is not uncommon anyway. And then this will become the go-to model of for the rest of the project. So this would be the point of reference that we're gonna use throughout the rest of it, and we're gonna use it to measure the correctness of everything that goes after it in the project's development. And that's it. Great to be here, and it was great to tell you this adventure. Whew.
Okay. So, are we gonna open to questions? No?
Yeah.
All right. I have one. By the way, when I'm speaking, if you can like avoid speaking, because the OBS is like bugged because of Pipewire.
Sure.
So one question I had when you were showing the table, right, when you did the memoization, is that when you do memoization, you're just swapping the looks to memory, right? So how is the memory usage of that? Because if it's a lot, like I suppose it's going to be big, but if it's shared like Fibonacci, I think that's reasonable, right?
I didn't profile it. I don't know how much memory it uses.
Mm-hmm.
That's actually a great question. Like 100 million iterations is a lot.
Yeah.
So maybe it's going to be significant enough to be a trade-off.
Because if it's like, here's what I'm thinking, right? If it's something like a Fibonacci, for example, that you roll back to the same number often, memoizing is not really bad because you're gonna use the same thing often, right?
Yeah.
Like in a high frequency. But since you got that gain, I suppose it could be either for the access is easier for things that are repeating consistently. So maybe the memory is not that bad, but yeah.
Yeah, something else that I was talking to Edu the other day is that maybe we don't need the entire table as well. Because if you think about it, if I'm calculating the iteration x, do I really need something other than x minus 1?
I see. So you want to split and segregate by recursion, something like this, right?
Yeah, so it would basically, instead of this entire, because if you do the math, because I didn't even explain this, because this is like numerical stuff related, but do you see the stages there? That is because some numerical methods you use more than one stage to do it. We are talking like up to 4 stages. So you are talking 100 million times 4. That's not a small thing, right? That's not a small thing. So maybe instead of having a table, having a line may be enough.
Makes sense.
Great question.
I have one more, which is
Oh,
you mentioned at some point you said about mapping to Haskell and the GPAC, right?
yeah.
Uh, I didn't really get what you meant when you said like you brought like you invoked something that would need to be proved like for that. Is that to see if you're implementing reliably the GPAC in Haskell, like encoding the computer?
Yeah, the thing is, there are some semantical things in Shannon's paper about GPAC that we didn't verify if they're actually being preserved when going to Haskell. It may be the case that, I don't know, laziness is breaking something. So we would have to take the properties of one thing and the properties of the other thing and see if they are not corrupting each other. If Jill, you have questions.
No, I have comments. I don't know. I'm not sure if I make them here to improve the thing or we switch to another channel to discuss it. I don't know. Up to you.
Marinho, any questions?
Not really. I have a comment as well, but
Okay, so Magueto, do we include the comments or not?
So I'll
Sure.
stop the recording and 1, 2, 3.